Okay, so we're going to take a look at the solutions chapter now. Um, and off we go. A solution is prepared by dissolving 2 grams of KCl in 100 grams of water. The solution in this solution, water is okay, so solution, solute, solid. Solution is a homogeneous mixture. It is the combination of both solute and solvent together. And in fact, it calls it a solution. So that is obviously not the answer. In this case, the solute is the thing that is being dissolved. This is in the lesser quantity. And in this case, the KCl is acting as the solute, the thing that is dissolved. So in sugar water, sugar is the solute. In salt water, salt is the solute. In something like a soda, you have like phosphoric acid, you have sugar, you have caffeine, all of those things are solutes. It is KCl is a solid, but that's not what we're dealing with. It is also ionic, but we don't care about that. And then solvent is the thing in greatest quantity. And in this case, the water is the thing that is in greatest quantity. There are 2 grams of KCl, there's 100 grams of water. This thing is in the greatest quantity, and therefore it's the solvent. If we multiplied this, if it were 200 grams of KCl, technically that would be the solvent. But that's what we're looking at. So water is the solvent in this case. So we'll call that E solvent. It's the thing that's doing the dissolving. It's the thing the solute is being dissolved in. All right, next up. When sucrose, C12H22O11, is dissolved in water, the sucrose is classified as a solvent. So it is dissolved in water. So technically, it is going to be the solute because it is not the solution and is not the solvent because it's being dissolved in the water. The water would be the solvent. The two together, the sucrose and the water, would be the solution. It is not ionic. You need metals or polyatomics, ammonium, in order to be an ion. And it is actually not an electrolyte because it doesn't dissociate. It's not ionic. So both of these have to be true for it to be um, an electrolyte. So in this case, it is also the solute. All right, now we're getting into some math. What is the mass percentage concentration of a solution of 10 grams of sodium chloride? Okay, dissolved in, it looks like 100 grams of solution. All right, so mass percentage is going to be, so my mass percent is the part over the whole, as any percentage is. In this case, it is going to be the mass of my solute over the mass of the solution times 100. I'm going to just take this a step further and say we have to recognize that the mass of solution is simply the mass of solute or solutes, if there's more than one, plus the mass of solvent times 100. So solute over the total stuff present. That's really important because some people just substitute in the solvent, and that is not proper. So we need to make sure that we're doing that correctly. All right. So in this case, the solute is going to be that 10 grams of sodium chloride. So 10 grams of sodium chloride is the solute in 100 grams of solution. Because it says solution and not solvent, the whole thing, 10 grams of sodium chloride plus 90 grams of whatever the solvent is, times 100. So 10 divided by 100 or divided by 100 times 100 is going to give you 10% by mass. So 10% by mass, that is incorrect, although it's 10, but it says molarity. 9%, it is a percentage, but it's not 10%. So C looks to be the answer. Let's just check the rest. 100%, nope. And that is also molarity. So 10% by mass. Next one, the mass percentage of a solution prepared from 500 grams of sodium chloride, 2.5 kilograms of water. So here we have two things. This is water. This is going to be my solute. This is going to be my solvent. And we're going to do the math. So percent by mass is the 500 grams of sodium chloride divided by the whole thing. So the whole thing weighs 500 grams of sodium chloride plus okay, so 2.5 kilograms is technically 2,500 grams. In order to add these numbers together, we have to make sure that they have the same unit. I can't add grams and kilograms. I have to convert one to the other. We could have converted the other two to grams, or kilograms, but that's more work than it's worth. So divided by 100. So in this case, it's 500. It's 500 divided by 3,000 times 100 gives me 16.6 repeating, or 16.7%. All right, 16.7%. Make sure you multiply it by 100 to get us to a percentage. So 16.7%. Remember, it's all of it. So it's the mass of the solute and the solvent. If this had been called 2.5 kilograms of solution, then we would have just used 2,500 as the solution, but it contains both of them. All right. Molarity. Okay, the molarity of a solution refers to, you're given the equation for this. In fact, in your crib sheet, you have molarity is equal to moles per liter, but you're not given the other part. The other part of this is moles of solute over liters of solution. So this actually mimics mass percentage the same exact way. It's solute over the solution. It's over the whole thing. So always the mass of your part, moles or grams, divided by the liters or the grams of your solution. So solute over solution, which is all of it. So moles of solute, we can eliminate grams of solute. Those are all moles of solute. Liters of not solvent, not 100 mils of solution. So we're going to call this one A. It's funny that people get this wrong. People who should be much better at this get this wrong. Moles of solute over liters of solution. All right, next up. What is the molarity of a solution that contains? Actually, I'm going to come back to this one. These two should be flipped. We're going to do this one first. 5 moles of KCl in 2 liters of solution. So molarity is moles per liter. Do I have moles of solute? I do in this case, 5 moles. Do I have liters of the whole solution? I do, 2.00 liters. So 5 divided by 2 gives me 2.50, and capital M is the unit, moles per liter, but capital M, anytime you see capital M, it's moles per liter in there. So it looks like B is the answer here. Now, the reason that I did 30, so this was 31, let's do 30 together. So again, it's asking for the molarity of the solution. Molarity is equal to moles of solute over liters of solution. Am I given either of those? I'm given a mass and I'm given liters of solution. So right away, I'm seeing, oh, okay, I do have 0.0500 liters. Now I just need moles. Well, you're not always given moles directly, but we can solve for it. So if I have 2.35 grams of NH3 times fraction, I want grams to go away, I want moles to remain. 1 mole of NH3 is how much? And nitrogen is 14. So let's just zoom in. We need the molar mass of this. Nitrogen is 14.01. Hydrogen, 3 times 1.01. So we should end up with, what's that, 17.04. So 17.04 grams. Grams cancels, and I'm left with moles. So 2.35 divided by 17.04 gives me 0.138. 0.138 moles. Now I have moles and I can plug that in. 0.138 moles divided by my 0.05. So when I do that math, I end up with 2.76 molar. 2.76, they're all molar. 147, 27.6, 0.276. It looks like A for this one as well. There we go. Okay. Moles of solute, liters of solution. So next up, how many moles of calcium chloride are in 250 mils of a 3 molar solution? Okay, so write out the equation. Molarity is equal to moles per liter. In this case, I am given 3.00 molar. I am given 250 milliliters, which is 0.250 liters. So 0.250 liters, and I'm looking for the mole quantity here. Okay, so this is just me cross multiplying, and we're going to end up with 3 times 0.25 to give me 0.75 moles of what I'm looking for. 0.75 moles looks like A for this one. You can use this molarity equation to give you volume concentration. Again, your volume has to be in liters because hidden in here, and I'm actually, maybe I'll just do this math over here. So if I cross multiply, I have 3.00 molar times my volume, which is 0.250 liters, is equal to, well, how many moles? That's what it's equal to. All right. So when I do this, I have to recognize that the units here, molarity is actually moles per liter. Liters cancels, leaves behind moles. So when you're multiplying these things, just remember that inside molarity, you have moles per liter. Okay. Moving on, how many milliliters of a 1.15 molar solution are needed to provide 0.665 moles of KOH? Again, we are going to use the same setup. Molarity is equal to moles per liter. And we know that the concentration was 1.15 molar, looks like anyway, and needed to provide 0.665 molar. 0.665 moles. So my question is, how many liters? And so we can do this math. I can switch those two. And ultimately, what you end up with is 0.665 moles divided by 1.15 moles per liter. Moles cancel, leaving me with liters. So 0.665 divided by 1.15 gives me 0.578. 0.578 liters or 578 milliliters. So 578 milliliters. So this one is E. Good, quick, simple, and off we go. What is the molarity of the solution obtained when 0.1 mole of copper sulfate are dissolved in 0.2 liters of solution? I will let you do this one, moles per liter. No, let's just do it. So 0.100 moles over 0.200 liters. This should just simply be 0.5 when you do the math, molar. So this should be A. There we go. Okay. Next up, 25 mils of alcohol is dissolved in water. The solution is diluted to a final volume of 125 milliliters. What is the final concentration of the ethanol? Okay, so we're seeing volumes instead of mass. And when we're looking at percentages, I gave you the mass equation, which was the mass of the solute over the mass of the solute over the mass of the solution times 100. Turns out that these things can be anything. I can do volume of solute over volume of solvent. And you'll actually see these on the back of a lot of medicine or hair products and those types of things, it's got these mass per volume ratios, but this is a volume ratio. So we can get rid of mass ratios because we're using volume. All right. The numbers are slightly different, but that's it. We're only plugging in different units, which cancel anyway. So let's see what we got. 25 mils of alcohol is dissolved in water. And the final volume of 125 mils is the final volume. What is the final concentration is the question. Okay, we can do this. So volume of solute is 25.0 milliliters divided by 125 milliliters times 100. Milliliters cancel. So as long as you're dividing those two properly, they're going to end up canceling anyway. So they should have the same unit times 100. So 25 divided by 125 gives me 0.2 times 100. So 20% by volume. So we're going to say that this is a 20% by volume. Perfect. All right. When 100 mils of a 6 molar solution is diluted. Okay, so right away, there's a dilution occurring. And so we need the dilution equation, which are also provided. V1C1 equals V2C2. This is the equation for a dilution. Volume and concentration, then a change is made and you have a new volume and a new concentration. So when 100 milliliters, which is my volume 1, at 6 molar, that's my first concentration, not my second. Concentration 1 is diluted to, this is the new volume. So we're going to call this volume 2, the final concentration. This right here is going to be my C2. So off we go. 100 times 6 molar. So 100 mils times a concentration of 6 molar is equal to a new volume of, I think it was 300 milliliters times concentration 2. Divide both sides by 300 milliliters. Divide by 300 milliliters. This is going to cancel out, leaving behind just C2. 300 mils, oh, not 300. The milliliters is going to cancel out, and now I do the math. The only unit that's left is going to be molarity. So the math is 100 times 6, enter, divided by 300, enter, 2.000, but 2.0 molar. It is 2 molar D. All right, onward. When 48 mils, okay, of a 12% mole by volume is diluted to 72 mils, there's a lot happening here. What is the new KCl concentration? All right, this one is way more complicated than it needs to be. We've got a handful of things happening here. This is kind of a ratio as well. There are a couple of ways that we can look at that, but let's take a look. So we can figure out, if I wanted to figure out this new substance, again, it is going to be, looks like we're doing mass over volume. Okay, so mass over the volume times 100. Again, the volume of the solution, mass of the solute. This is way more complicated. I promise you won't have anything like this, but it's worth kind of looking at. But it doesn't matter, mass, volume, mass, volume. It is mass over solution. All right. So we know for this first situation here, we happen to know the current situation is, let's see. So the first situation is 48 milliliters all over some mass of solute. We don't know, they didn't mention the solute. Times 100 equals 12%. So this is the information that we have. And then it is diluted. Keep in mind when you dilute something, if I dilute it to 72 milliliters, I don't change the amount of solute, right? So if I have some salt water, KCl in this case, if I have some salt water and I add more water to it, the amount of solute is going to stay the same. So what we're going to do is we are going to solve for the solute and we're going to keep that consistent. Okay. So we know that we're not adding any more solute. We are adding more water though. Okay. So if it's at 12%, we can solve for the mass of the solute. In this case, it's KCl. So divide by 100 to get rid of this, and that's going to give me 0.12. Okay. Now it is just simply 0.12. Let me just rearrange this. 0.12 is equal to these two. Cross multiply, so 0.12 times 48 gives me a value of 5.76. 5.76, and that would be grams. Good. So way more complicated again than it needs to be. My mass of solute for the new solution is 5.76 grams. That does not change, right? By adding more water, that doesn't change. My new volume was 72 milliliters times 100. I want to know what the new percentage is. So 5.76 divided by 72, enter, times 100 gives me 8%. So 8% D is the answer for this one. It's a good little problem, way more complicated than it needs to be. All right, moving on. And the rest of these look like they are all stoichiometry. I know because I am given information about one chemical and I am asked to solve for another chemical. So I know that it is going to be a stoichiometry problem. So I'm given information about that, the aluminum, and I'm asked to solve for this. Okay. So this is a stoichiometry problem. When I am converting 2 moles from grams, okay, so when I'm going from grams to moles, I'm using molar mass of aluminum. Then I'm going to switch to moles of what I'm looking for, H2SO4. This is done with molar ratio, which I have highlighted below. And then when I'm going to moles to volume of a solution, which I should do this way, to find volume, we do this using concentration. Because concentration is in moles per liter, it allows us to convert moles of what we have to, or what we want, to liters of what we want. So that is the 4-step process here. So we are going to start with 1.26 grams of aluminum times, I'm probably going to need more. Oh, I got enough room. 1.26 grams of aluminum times fraction. I want grams of aluminum to go away. I want moles of aluminum to remain. 1 mole of aluminum is equivalent to, let me look up this P table. Aluminum weighs 26.98 grams. 26.98 grams per 1 mole. Grams of aluminum would cancel. This is the molar mass of aluminum. Next, times fraction. Let's switch. Okay. Times fraction. I want moles of aluminum to go away, and I want to switch my chemicals now to H2SO4. So this is going to be my molar ratio. Where do I get that? I get that from the balanced chemical equation. 2 moles of aluminum to 3 moles of H2SO4. So 2 moles of aluminum to 3 moles of H2SO4. Moles of aluminum cancel. Right now, my unit is moles of aluminum, but that's not what I'm interested in. One more step, times fraction. This is where I'm using concentration of my solution. Moles on the bottom, liters on the top. 1 liter of H2SO4, that's the number right there, is 1.24 moles per liter. That's the concentration, 1.24 moles per liter. Moles cancel, and I'm left with liters. And it looks like it wants the answers in milliliters. So let's get the answer in liters, and then we're just going to convert it in our heads. So 1.26 grams of aluminum divided by 26.98, enter. Oh, all right, let's try this one more time using my calculator. All right, here we go. 1.26 divided by 26.98, enter, times 3, because I'm multiplying the top, divided by 2, dividing the bottom, divided by 1.24 moles per that 1 liter, and you end up with 0.0565. 0.565 liters is my unit. I'm going to move the decimal 3 times. 1, 2, 3. 56.5 milliliters is going to be my answer. 56.5 milliliters. There it is. B is our answer. More complicated, but not really. When we're doing stoichiometry with a solid, we're using molar mass. When we're doing stoichiometry with a gas, we use PV equals nRT. When you're doing stoichiometry with solutions, you use concentrations, and that's pretty much it. Next one, how many grams of aluminum will react with 25 mils of 122 molar H2SO4? Again, I am looking for aluminum. I'm given information about H2SO4. And so off we go. Instead of giving you grams, I give you volume for gases or for liquids. And we're going to do the same exact idea here. There's my H2SO4, there's my aluminum, and off we go. So I'm going to start with volume, 24.0 milliliters. Okay. We want to convert this to liters whenever we're dealing with molarity. So I'm going to rewrite 0.0240 liters of my H2SO4 times fraction. I want liters to go away. I want moles to remain. I need more room here, so I'll get rid of that. This is concentration of my H2SO4. 1 liter is equivalent to 1.22 moles, because that's true because the molarity is 1.22 molar moles per liter. Liters cancels times fraction. This is moles of H2SO4 to moles of aluminum. And according to the balanced chemical equation, 2 moles of aluminum for 3 moles of H2SO4. So 2 moles of aluminum for 3 moles of H2SO4. Moles of H2SO4 goes away. I've got moles of aluminum times fraction, moles of aluminum on the bottom, grams of aluminum on the top. 1 mole is equivalent to 26.98 grams of aluminum. Again, molar ratio. And then this is molar mass of aluminum. That's it. Convert from what you have, volume or mass, to moles, switch the chemicals using molar ratio, and then go back to what you need. And so now we do the math. 0.024 times 1.22, enter, times 2, enter, divided by 3, enter, times 26.98, enter. So we end up with a mass of 0.527 grams of aluminum. 5.2, so 0.527 grams of aluminum. There it is. C is my answer. Okay, so far so good. I think we've got one more. This is about as complicated as they get. Okay, so last one. I think it's the last one. This one here, I'm going to leave this one up to you. But here we go. Again, I want to point out the fact that when you're doing these conversions, it's always starting with a volume or a mass, converting to moles, switching the chemicals using molar ratio, and then going back to grams or volume based on what you have. So how do I know this is stoichiometry? This is the information I'm given, Excess aluminum just simply means I don't care about the aluminum. It's not interfering with the reaction. There's enough there to react. How many liters of H2 are formed? Okay, so that's what we're looking for. And we're given other information. So it's asking about hydrogen. There's the hydrogen. There's the H2SO4, 23 degrees C, and a pressure of 745. Okay, so the idea here is I am going to start with what I have, 35 milliliters. Again, we're going to convert to liters of H2SO4. And I want to convert to moles. Liters of H2SO4 goes away. Moles of H2SO4 remains. This is going to be concentration of H2SO4. So 1 liter is equivalent to 0.92 moles because that's the concentration, moles per liter, molarity. At this point, liters of H2SO4 cancels, and I'm left with moles of H2SO4. But that's not what we're looking for. We're looking for moles. So we want that to go away. We're looking for moles of H2. According to the balanced chemical equation, 3 moles of H2SO4 is equivalent to 3 moles of H2. Well, that makes life easy. It's 3 to 3 or 1 to 1. So math is done. We don't even have to do that last step. But importantly, we now have moles of what we're looking for. Moles of H2. So off we go. So 0.035 times 0.92, enter. And times 3 divided by 3 gives us the same answer back, 0.0322 moles of hydrogen. So now what? Because it's a gas, we are going to use PV equals nRT. So PV equals nRT allows me to convert back and forth between volume and moles. So what I'm looking for is volume. I just solved for moles. I have R, I have temperature, and I have pressure. So now we're just going to plug into this and solve for what we need. So my pressure, by the way, 745 times fraction, I need to convert this to atmospheres. We always need to convert it to atmospheres. Millimeters of mercury cancels. I'm left with atmospheres. 745 divided by 760 gives me 0.980. So 0.98 atmospheres. That is my pressure. We are looking for volume. We have moles down here. So 0.0322 moles. My R value, which you're provided, this is 0.0821 liter atmospheres per mole K. And then finally, temperature plus 273 gives me 296 Kelvin. And off we go. I've got atmospheres. I've got moles. I've got, oh, I don't have liters. I have Kelvin. So my answer should be in liters. So I'm just going to divide both sides by 0.98. So divide by 0.98. Off we go. So 0.0322 times 0.0821, enter, times 296, enter, divided by 0.98, enter, gives me 0.979, so 0.80-ish. Well, I can round it. 0.798. 798 liters of hydrogen gas. 0.798. There it is. Close enough. A is the answer there. Stoichiometry, always the same way. Convert to moles, molar ratio to switch, convert back to volume or grams. And there's one more, but I'm going to leave it up to you. And then acids and bases, the last one. Again, acids and bases is not on this exam, just through solutions. All right.